straight on to basic systems and field feedbacks. So if you want to go straight on, smiley face, please. Right. Oh, that's good. That's all of you. Okay. Moving right along then. Basic system and feedback. First thing we'll talk about is a system. It's one of those words we use all of the time. A system is something which consists of more than one component. Now what that means is everything is a system. We as engineers, we do this system thinking idea. We lump things all in together so that we don't think about the details, but as engineers we're capable of thinking of the details. So you walk into a room and you turn the lights on. Now the lights is a system. Most of you, I'm guessing, are electricians, which means you know the things inside the light. There's a lot involved. There's wires, there's switches, there's ballasts and capacitors, and there's a switchboard. In fact, there's circuit breakers, all the way back to Western Power, or wherever it is you're getting your power from. There's a lot involved in the system of turning on those lights. We don't think about that. We just walk into a room, flick the switch, and the lights come on. We call that black boxing, where we say we don't really care what's involved. All that we care about is the outputs and the inputs. So we have some inputs, which are the switch and electricity, and we have an output, which is light. That's all we really care about when it's all working. Now, quick aside, as a general rule, whenever we're doing system drawings, if we're going in the normal direction, which means we're going forward in time, then we have in on the left and out on the right. So that's used throughout. That's used in PLC programming and all sorts. In the second part of the course where we do programming, you'll see in on the left, out on the right. Now, most people do black boxing quite happily, and the lights are something that has a switch and power, and they come in, they flick the switch, and the lights come on. If the lights don't come on, they flick the switch off and flick the switch back on, and frankly, most people are then stumped. As electricians, what we normally do at this point is we have a look inside that box, and we sort of unpack the box very quickly in our own minds, and we find the bit that's broken, and then we fix it. So the difference between us and most people is that we're capable of looking inside that box, finding the components, finding the broken component, and fixing it so the lights do come on. One type of black boxing, of course, is the P&ID drawing we just discussed, where effectively we have flow valve, FV100. What this tells me is that I have a flow valve. It's on loop 100. It's been called number 100. It's flow valve 100. There's no line through it, so I know that it's out in the field somewhere. There's loads I don't know about it. I don't know the manufacturer. I don't know the colour. I don't know the size. I don't know anything about that valve apart from the fact that it's a flow valve and that it's out in the field somewhere. And, you know, I don't need to know anything more about that valve. Over here I have a thing FT, flow transmitter, and it says it's a mag flow meter, and all I know about that is that it lives out, it hasn't got a line through it, so it lives out in the field. Once again, I don't know the manufacturer or the size or anything. Signals are drawn between these instruments. Now, the types of signals we send from one instrument to the other, in the olden days, it used to be in air, and we used to send the pneumatic signal, and we used to send 3 to 15 psi, where psi stood for pounds per square inch. PSI. Nowadays, we've gone to the SI, or metric system, and in SI we send 20 to 100 kPa. Now it turns out that we're really lucky, because 3 psi just about equals 20 kPa, and 15 psi just about equals 100 kPa. So that works out really well. 3 psi is 20 kPa, 15 psi is 100 kPa. So what that means is 3 to 15 psi is the same as 20 to 100 kPa. With the advent of PLCs, we needed to send electrical signals. At first, they started sending voltages, 0 to 10 volts or 1 to 5 volts. The problem you have with voltage is volt drop. Volt drop is a big problem. To get round that problem, rather than sending voltage, what we send nowadays is milliamps. With milliamps, everywhere in the circuit you must have the same current because it's got nowhere else to go. So we use milliamps so that we don't suffer from the problem of volt drops. Now, here's a question. Why do we use elevated zeros, as it's called? Why do we use 4 to 20 milliamps? Why do we use 20 to 100 kPa? Why not use 0 to 100 kPa or 0 to 20 milliamps? Yep, you've got it. If you know that the signal's going to be 4 to 20 milliamps, if you measure it and you get 0 milliamps, that means it's broken. So we use that to check the equipment. We use that to check that the circuit's actually in place. Because 0 milliamps or 0 kPa, that's a sure sign that it's broken. In more modern times, of course, we're going away from the so-called analog signals. We're going to digital signals. This is where instruments are effectively computers and they talk to each other digitally. Different types of signal you get. The first type of digital comms is called HART. Now, HART is interesting because HART just works on the existing 4 to 20 milliamp cables. So with HART, you can have a 4 to 20 milliamp signal and also talk digitally to it. Other systems out there are Field Bus and Profibus. There's a system called LON. There's Ethernet, which is your standard blue wire into a modem, into a port really. And there's C-Bus. Now, have any of you used any of these systems before? Okay, so I'm guessing none of you have used these systems. Well, digital signals are the new way to go. Oh, you've used HART, that's good. Now, digital signals are the way to go. They're the future. Unfortunately, you've got people like me. I'm a dinosaur. I like the old-fashioned gear. I like the old 4 to 20 milliamp stuff. The reason why I like the old 4 to 20 milliamp stuff, and the reason why installation engineers don't, is when we look at the topology. 4 to 20 milliamp old-fashioned comms is wired up in what's called a star topology, so that you have the instruments out here, and then they all get wired back to the PLC in a big star topology. Now this involves pulling a lot of cable. You pull a lot of cable, and with that cable you have to have conduit and tray and trunking. So install-wise, it's a lot of work and it's a lot of expense. With modern systems, you don't need to send a cable to each instrument. What you do is you send one cable from the control room out to the first instrument, and then you just wire from that to the second instrument, from that to the third, to the fourth, to the fifth, all the way down the line, until you'd be wiring to, say, this instrument over here, which might be anything like, no, that's the wrong thing. This might be instrument number 125, for instance. Now, this allows you can have 125 instruments in some cases. In other cases, it might be 62 instruments. But you could have loads of instruments all on one piece of very thin, cheap cable. Install-wise, it's a dream. The install engineers love the digital system. They just pull one cable between everything, and then they just turn it on, and everything comes up with a little happy smiley face, so that when they look at it on their diagnostics screen, they end up with lots of little happy smiley faces, which means that the instruments are all happy. The problem you get with digital signals is when something goes wrong. In this case, I've got a fault on this instrument here, but it's not showing as a fault on that instrument there. This instrument there is still coming back with a happy smiley face. The problem is showing on these other instruments. This instrument here is coming back with an unhappy face. He's not communicating. This one here is also not communicating. So one instrument, this instrument just here, can cause these two instruments to stop working. Now that's why I don't like digital systems, because now we have a problem. The first thing you do naturally is you come in and you replace one of these instruments. And lo and behold, one of two things will happen. Either the fault doesn't go away, or even worse, the fault goes away. Because the reason the fault went away is because you powered everything down. And as you know, when you power things down and you power them back up, the fault generally disappears. So the worst thing that can happen is we change this instrument and the fault goes away, or at least it seems to. Because like a day later, the fault comes back. So we come in again and we say, oh, we changed that on Thursday, maybe we'll change this one this time. So we come in and we change this instrument. And if we're really, really unlucky, the fault goes away. But we haven't fixed it. The only reason the fault went away is because we switched it off and back on. So 2 days later, the fault is back. So now we're running out of ideas. Now what we do is we start changing the instruments one at a time. And depending on which end we start at, we could change 125 instruments, or we could change 5 instruments. But either way, it's going to be a very bad fault-finding experience. Because, of course, every time we power the stupid thing down and back up again, it starts working again. We don't know it's faulty until 2 days later. So you end up with a very bad reputation because it's taken you 6 months to find one faulty temperature sensor. Even worse is the fact that the fault here might not be because of the instrument. The fault there is probably caused by the fact that somebody installed a VSD. And a VSD, for those of you that don't know, is a variable speed drive. And variable speed drives are absolutely notorious for transmitting radio VSD throughout your mine site. And if somebody installed a VSD in the room just next door, you can go through and you can replace all of those instruments, and yet the fault will not disappear. Because the fault isn't actually the instrument itself. The instrument itself is fine. The fault is the VSD that's been badly installed. Now later on in this course we'll be talking about VSDs and we'll be talking about how you should install a VSD so that it doesn't stop the communications working, because this is a very, very common fault. So, for these reasons, I don't like digital setups. I like good old-fashioned 4 to 20 milliamp star topology loops, because I know that if I have a good old-fashioned star topology loop and this instrument here goes down, then all I need to do is replace it. Furthermore, if this instrument here goes down, I can say to the apprentice electrician on site, well, stick your voltmeter on it, what do you get? And if he says I get 0 volts, well, I figure it's that instrument. Whereas the digital stuff, the first-year apprentice on site hasn't got a clue, and quite frankly, neither have I. Yeah, I know some of you are saying, or at least John's saying, that if everything is addressed properly, it should let you know which one is broken. But in my case here, none of them are broken. The fault is not with the digital system at all. The fault is with a VSD which just happens to be 2 doors down in another room. And that VSD is actually the fault. So what can happen is that VSD, when it's running at 37 Hertz, can stop this instrument talking. And when it's running at 39 Hertz, it stops this instrument talking. And when it's running at 34 Hertz, it stops this one talking. And that's the sort of faults you get with VSDs. You get these weird and wonderful communication faults where different things stop talking on different days.